Hi guys, and welcome to the fourth video. Today we're going to talk about conditioning. So something you all already know how to compute. Suppose we roll 2 dice, and we want to know the probability we get a 9 or higher. And the answer is 10 out of 36. But suppose we change the scenario a little bit, and we drop the die one at a time. So on the first die we get a 3. What's the probability of getting a 9 or higher? Well, you can intuitively figure this out. If the first roll is a 3, the only way to get a 9 or higher is to get a 6 on our second roll. So to get a 6 on our second roll, we have a 1 out of 6 chance, which is 6 out of 36. And that's less than 10 out of 36. So if the first roll is a 3, then our probability has gone down that we're going to get a 9 or higher. So as we gather data, the probability of a particular event occurring could change. So we'd like to find a formula for computing the probability of an event based on other information that we've gathered. And the mathematical notation for this is going to be P of A vertical bar B. And that vertical bar on the left of the bar is the event that we're computing the probability of. And on the right of the vertical bar is the events that we know occurred. So the way that you read that is the probability of A given B. Intuitively, we want a couple of things to happen in the formula. So since we know that B has occurred for sure, the probability of B given B should equal 1. Also, recall from set theory that any set A can be written as A equals A intersect B union A intersect B complement. That is, it's all the points that are in both A and B and all the points that are in A but not in B. So knowing that B occurred, we can throw away the A intersect B complement part, because if the outcome has to be in B, then it's not in B complement. And so the formula that's going to satisfy this is the probability of A given B is defined to be the probability of A intersect B over the probability of B. This agrees with our first intuition because the probability of B given B equals 1 will be true. So if you plug in B for A, and remember that B intersect B is just B, then you'll see that this identity is always true. Also on the numerator, you can see that we've thrown away the probability of A intersect B complement part. So we only take into account the probability of A intersect B. That is, points or outcomes that are in both the sets A and B. So if we go back to our example, let D be the set 1 through 6, which represent the outcomes of one roll of the die. And omega, our sample space, will be D cross D, where the first coordinate represents the first roll, and the second coordinate represents the second roll. So letting A be the event that we roll a 9 or higher, we could roll a 3 first and then a 6, or a 4 first and second to 6, or a 5 first and the 6 second, and so on. And so A just lists out all the different ways that we could roll a 9 or higher. Let B be the event that the first die rolls a 3. So you could roll a 3 and a 1, or a 3 and a 2, or a 3 and a 3, and so on to a 3 and a 6. So all of these points represent an outcome where the first roll is a 3. A intersect B is 3, 6, so that's the only point common to both sets. That would be the point. Remember that an intersection is an AND, so that's the point where you roll a 9 or higher and roll a 3 in the first coordinate. There are 36 points in omega, and each is equally likely. Therefore, the probability of A intersect B is 1 out of 36, and the probability of B is 6 out of 36, because if you go back a few seconds, there were 6 points inside of the set B. Now we can use this formula to verify our intuitive computation from earlier, the probability of A given B is the probability of A intersect B divided by the probability of B, just because that's the definition that we gave to that notation. And now plugging in, this equals 1 out of 36 divided by 6 out of 36, and the 36's will cancel. So this is 1 out of 6, which does agree with the intuition. You can rearrange this formula algebraically to get the product rule. So the probability of A given B is listed there again in terms of its definition, and multiplying the probability of B over to the other side, you get the formula that the probability of A and B is equal to the probability of B times the probability of A given B. So what's the probability that we roll a 3 and our total is a 9 or higher? Well, we know that the probability we roll a 3 is a 1 out of 6. And intuitively, we knew that the probability we rolled a 9 or higher, if we know that our first roll is a 3, is 1 out of 6, because the second roll has to be a 6. Therefore, the probability of rolling a 3 on our first roll and getting a 9 or higher is the probability that we roll a 3 times the probability that we roll a 9 or higher knowing that our first roll is a 3, which is 1/6 times 1/6, or 1 over 36. And again, if you go back a few seconds, you'll see that the probability of rolling a 3 and a 9 or higher was computed to be 1 over 36. So remember that the probability of A is equal to the probability of A intersect B plus the probability of A intersect B complement. That is, you can add the probabilities of A and B happening plus the probability of A happening and B not happening. By the product rule, we can replace those intersections in the computation. So the probability of A is the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. And now we're going to do a little computation. So the probability of A given B equals the probability of A intersect B divided by the probability of B, because that's the definition of probability of A given B. And that equals the next term here because we just multiply by the probability of A on the numerator and the denominator. And then the probability of A intersect B divided by the probability of A is equal to the probability of B given A. So that probability of A intersect B is going to absorb one of the probabilities of A in the denominator, and then in the numerator we have the probability of B given A on the far right. And that's Bayes' rule. So the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. And oftentimes you'll see it also expressed with the probability of B expanded in the denominator, and that's just according to that second point up there that says by the product rule, with B and A reversed. So why is this important? We want to know the probability that A happened knowing that B has already occurred, but a lot of times we won't have that information. However, we will have the probability that B happened knowing that A occurred. And the point is that we can reverse the information. So if we want to know that A happened, want to know the probability that A happens knowing B, we can actually flip around the information and suppose that we know A and find the probability that B happened, as long as we can also compute the probability of A occurring and the probability of B occurring. So this is a very important rule, and it comes up in applications a lot of times. So, for example, doctors know what symptoms are correlated with what diseases. So, for example, he knows if you have a cold, you're going to have a runny nose. Of course, a lot of other things could also cause a runny nose, but a cold is one of those things. So, as a patient, you come to your doctor and you have a runny nose. The doctor has to ask, does that runny nose imply or indicate that you just have a cold? Or could it be something else? Another situation could be a biased teacher. So a teacher that's biased might give a certain group of students higher scores. there's a particular teacher named Mrs. Jones, and she has her class data observed by a statistician. And the statistician notices that the blue-eyed students all got higher scores. So should the statistician say that Mrs. Jones is biased? Notice that we know if she's biased, then she might give blue-eyed students higher scores. But what we actually observe is that blue-eyed students get higher scores. The question is she biased? And last example for now, a scientific experiment. So a physicist is studying properties of hydrogen using tanks in a hydrogen lab, and the results differ from what was predicted should happen, but they could be explained by a gas leak. So that is, these results would occur given that there's a gas leak. What's the probability that there is a gas leak given that these results were obtained? So oftentimes we want to know the probability of one event, or know whether or not one event occurred given a second event, but it's a lot easier to know the probability that the second event happened given the first. So the takeaway to this is Bayes' rule is a very important rule, and it comes up in applications pretty often. Alright, God bless. I'll talk to you guys in class.